All right, folks, last learning goal of this section. Let's go for it. It's on the photoelectric effect. Okay, let's navigate down to the slide, all the way down to the end. Here we go. So the photoelectric effect describes the emission of electrons from the interaction of electromagnetic radiation of a solid, typically under high vacuum. So I've got two kind of cartoons here describing that. So in both of these cartoons, we're irradiating potassium metal with light, with electromagnetic radiation. In one case, we shoot a 700 nanometer photon at the potassium metal and nothing happens. In the other case, we shoot a UV photon, a 200 nanometer photon, and that causes the ejection of an electron. So we can write a chemical reaction that describes that. Potassium solid plus H nu, right, light, makes our K plus ion and our ejected electron. So why does the 700 nanometer photon not do it, but the 200 nanometer photon does? Well, that's because 1 mole of potassium requires 419 kilojoules to remove 1 mole of electrons. And so if we work backwards with that number, we would find that the 700 nanometers is not enough energy to induce ionization. So nothing happens. As it turns out, the 200 nanometer photon contains more than enough energy to not only ionize the electron, but to also give that electron some additional kinetic energy. So the equation for the photoelectric effect goes as the following. The kinetic energy of the electron, which can be described by 1/2 mv squared. So it is a particle that's flying off the surface. It has mass, it has velocity. That is equal to the incident EM radiation. So that is the incident EM. And we're writing that as H nu, or it could be written as Hc over lambda, right? It's the energy of the incident radiation. And this phi is known as the work function. So that is the energy required to ionize the electron. And we notice here when these are both equal to each other, our electron will have 0 kinetic energy, and we call that threshold ionization. But when the incident EM radiation is more than the work function, there will be excess energy given to that electron in the form of kinetic energy. So we can look at this graphically in the following way. So if we look on the y-axis, kinetic energy on the y, and frequency of the incident radiation on the x, and noting the equation here, we could write this in the form of a line as y equals mx minus b. And what we can see here, right, the x is frequency as noted. If I trace this all the way down to where it crosses the intercept, you can see that's why it's a negative b. So now this gap right here, that represents the work function. And then now, as you notice, the slope for all of these are the same. So the slope of this effect is Planck's constant. So this is actually one way we can determine the value of Planck's constant using modern instrumentation. I should have had a periodic table in front of me here, but if we notice now, we can trace this back and look at what the, using the tracing it back, we can figure out what those threshold ionizations would be, or the work functions. So those are these values right here. So you can see rubidium is 2.09 eV, potassium is 2.25, sodium is 2.3. So this is following the trend of the periodic table, where we see increasing work function as we go up the table and increasing work function as we would go over on the table. So this is pretty cool. It's a way to determine those periodic trends. If we look at this effect on our energy level scale, we can see here in the case where our incident radiation is less than the work function, like the example given, right? So let's suppose that that was 700 nanometers. You can see that that incident radiation was not enough to match the work function. However, in the other example I gave, where our incident radiation was 200 nanometers, you can see not only is that more than enough to surpass the work function, but now there's excess energy which is given to that electron in forms of its kinetic energy. Okay, so we'll review this technique a lot more as we get into our section on spectroscopy. As it turns out, this technique is a fantastic diagnostic for quantifying or identifying molecules on a surface. Okay, folks, that's it for this section. I'll see you in the next one.